And we are live. Good evening and good day, everybody. Welcome to episode 21 of the Ask Abhijit show. So, as you know, today we are doing the science and astrophysics episode, and this is where you get to ask me any question you have. And no question is too silly or too stupid. All questions are good. I am not your school teacher or professor. I will take your questions and I will answer them all. So keep your questions coming. And as always, you have asked me a bunch of very interesting questions. And I have picked a few of those today. So let's get into it, shall we? Let's do it. Let's begin with question number one. And this question is by Priyansh Bansal. We know that the Andromeda galaxy is 2.5 million light years away from us. So, how can we know its current position if the light from it is 2.5 million years old? How can we know when the collision will occur? Okay, so it's an interesting question. How do we know the distance between galaxies? How do we know how far a certain galaxy is away from us? So there is something in astronomy called a standard candle, and there are a couple of types of standard candles. So there is one class of stars called the Cepheid variables. So these are extremely luminous stars, between 10,000 and 100,000 times more luminous than the sun. And these stars, they pulsate in a predictable way. So the luminosity goes up and goes down in a periodic fashion, in a predictable way. And the period of oscillation or pulsation is related to the luminosity of the star. So if we know the period of pulsation of the star, then we know the luminosity. And depending on how dim or bright the star is, we can actually calculate its distance from us. So because the apparent luminosity decreases with the square of the distance. And these stars are so bright, then we can actually observe them in other galaxies, like the Andromeda galaxy. So that's how we are able, by observing such stars, the Cepheid variable stars, to determine the distance between us and the Andromeda galaxy to a very high degree of accuracy. So this is a standard candle, basically. Okay, this kind of star is called a standard candle. And there's another standard candle, which is the type 1a supernova, which also has a very specific luminosity. So based on such astronomical objects, we can actually determine the distance between us and something like the Andromeda galaxy. So we know how far away it is. It's about 2.5 million light years away from us. And we know at what distance it is coming towards us, because there is something called redshift and blue shift. So when something is redshifted away from us, it means it is receding away from us. It's going further away from us. And when something is blue shifted, it means it's coming towards us. So the Andromeda galaxy, we know it is coming towards us at a certain speed. And that's the basis on which we are able to calculate approximately when it's going to collide or merge with our own galaxy. So that's how it works. That's how the astronomical observations and calculations are done. Aryan asks the silliest question, but what happens when someone goes below the Mariana Trench? Not humans, of course, because of the pressure, but some machine. Can we find another life form? So for those of you who don't know, the Mariana Trench is the lowest known place in the seafloor, on the seafloor. So it's about 11 or so kilometers below the surface of the ocean. It is so deep that if you placed Mount Everest in it, there would still be a couple of kilometers or so left. So the top of the Mount Everest would still be two or 2.5 kilometers below the surface of the ocean. That's how deep the Mariana Trench is. And I think the pressure, the water pressure at the bottom of the Mariana Trench is about more than 1,000 times the atmospheric pressure that we experience over here on the surface of the planet. So it's very deep, and the water pressure is very, very high. And yet people have gone to the bottom of the Mariana Trench in special submersibles, special submarines that are purpose built to withstand that sort of pressure. And we have also sent robotic submarines to this place. And surprisingly, we have observed life forms there. Certain kinds of fish have been observed, certain types of crustaceans have been observed, giant amoebas have been observed. So, yes, life does exist even at that intense depth and that incredible pressure. So, that's the thing about life. Life apparently is able to survive almost anywhere on this planet or inside the planet. I mean, recently they have found certain very ancient rocks that are millions of years old, and it seems that there are bacteria thriving in there. I mean, living in there. They are not exactly thriving, but they are there inside this incredibly ancient rock, and they are not dead. They are dormant, but they can come back to life. So that's the strange thing about life on Earth. It survives somehow, anyhow. So I hope that answers this question. Okay, Siddhant asks, the photon is a packet of energy. So, what is that energy, and what is the thing that's stopping the energy to come out of the packet? So, it's a bundle of electromagnetic radiation. It's a bundle of electromagnetic energy, and there's nothing that's actually stopping it from coming out of the packet, because photons do lose energy. So there's something called the gravitational redshift. So when a photon passes near a massive object, the gravity of this massive body actually can decrease the energy of the photon. It can redshift the photon, which means its wavelength becomes longer, in which case it loses energy. And there is something called, I mean, the photons are also redshifted because of the expansion of the universe. So let's say a photon is emitted from a distant galaxy. It travels towards us, and as we know, space-time is expanding. The universe is expanding, and what we find is that the photon, when it reaches us, is redshifted, so it has lost energy. Its wavelength has become longer, so it loses energy, and this brings into question the principle of conservation of energy, because energy is supposed to be conserved in the universe. And yet you have these photons that are getting redshifted, and these photons are losing energy. So the question arises, where does this energy go? And it's perplexing, but the answer seems to be that the photons are footing the bill of the expansion of the universe. So the energy is going into the creation of new space-time in the expansion of the universe. So that's an interesting little tidbit. So photons do lose energy. The wave packet, the quantum mechanical wave packet, does lose energy, and it does elongate in wavelength. And a photon can even be redshifted out of existence by either the expansion of space-time or by the presence of a massive object near, if it passes near that. So yes, photons do lose energy. The energy does seem to leak out of the packet by various means. Isn't that interesting? Okay, next question. Akash asks, does absolute zero occur naturally in the universe somewhere? And what's the average temperature of the universe? Good question. So first, let me answer the question of the the average temperature. The average temperature of the universe is about 2.73 or so Kelvin, which is minus 270 approximately degrees Celsius. So this is the temperature of the cosmic microwave background radiation, which is the earliest light that was produced in the universe. So it's kind of the remnant of the Big Bang, and that was once very high energy light, but now it's extremely, extremely cold. So it's just barely above, it's 2.73 Kelvin above absolute zero. So that is the average temperature of the universe. So, does absolute zero occur naturally in the universe somewhere? No, it does not. Absolute zero is impossible to reach. And the reason for this has to do with the amount of work that's necessary to remove heat from any substance. So, the amount of work you have to do to remove heat from a substance increases substantially the colder you try to go. So, to reach 0 kelvins, we find that you would require to put in an infinite number of work, and therefore it's impossible to reach 0 Kelvin. We are able to reach very close to 0 Kelvin in the lab by cooling various gases and atoms, but it's impossible to reach 0 Kelvin. And even if you were to reach 0 Kelvin, there are quantum mechanical effects that ensure that the temperature is never really 0 Kelvin. There is still something called 0 point energy left behind. So absolute zero does not occur naturally in the universe anywhere. It can't even occur artificially, because you cannot do that amount of work in order to bring a substance or a body down to absolute zero. Interesting. Good question. Okay, yeah, this is a related question. So, just as the universe has a lower limit of temperature, which is absolute zero, does it have an upper limit of temperature too, beyond which the temperature cannot rise any further? That's another excellent question. So, the theoretically highest achievable temperature is the Planck temperature, which is of the order of 10 raised to 32 Kelvin. So, that's an incredibly insane amount of temperature. It's incredibly high, 10 raised to 32 Kelvin. And it is, according to the Big Bang theory, when the universe was about 10 raised to minus 43 seconds old, which is the Planck time, that is when the universe had this temperature, 10 raised to 32 Kelvin. So that is the theoretical upper limit of temperature. We are not able to achieve anything close to that in the lab or anywhere else. I think the highest that has been achieved in a lab or in any instrument has been around 1 trillion Kelvin, which was probably something that was achieved in some kind of a collider, a linear accelerator, or a collider. But the Planck temperature is way, way beyond that. So it's almost unimaginable. But that's the theoretical maximum that can be attained in the universe. Aruni asks, are black holes denser than a neutron star? What could possibly happen if a black hole and a neutron star would collide? Black holes are indeed denser than neutron stars. Neutron stars are the densest objects in the universe, apart from black holes. So a neutron star typically has a mass of 1.4 times the mass of our sun, and it is so dense that its radius is typically of the order of 10 kilometers or so. So imagine something more massive than the sun, 1.4 times the solar mass, and it has a radius of about 10 kilometers. So that's how dense, that's how compact a neutron star is. And black holes are denser than neutron stars. They are basically they are so dense that even light cannot escape from them. So that's what a black hole is. It's denser than a neutron star. What would happen if a black hole and a neutron star would collide? They would give off a big burst of gravitational waves, a tsunami of gravitational waves, and then the black hole would absorb the neutron star, and the result would be a larger black hole whose mass is the mass of the black hole plus the mass of the neutron star minus the energy that was radiated out in the form of gravitational waves. So that is the result of such a collision. Good question. And again, this is the same questioner, Aruni. Are black holes eternal? And will they keep getting bigger and bigger and never die? If a black hole can die, how would they possibly die? Silently or with a big explosion? If they can explode, what would come out of a black hole explosion? Very good questions. So first of all, the space is silent. There is no gas, and therefore there is no sound. So even if you have an explosion in space, you can't hear it. It's not audible. You can simply see it. You can see the light that's output from the explosion in the form of various frequencies of radiation: ultraviolet, infrared, gamma rays, X-rays, etc., and visible light. And if something is ejected out of it, it may hit you if you are close enough. So that's the kind of explosion you would see. Now, are black holes eternal? Well, some black holes seem to be eternal, some are not. So a black hole has a temperature, and the temperature of a black hole is inversely proportional to its mass. So the larger a black hole is, the more massive it is, the colder it is. And the smaller a black hole is, the hotter it is. That's how it works. Now, a hot black hole evaporates, it gives off radiation, and therefore it will decrease in size. A cold black hole, if it is colder than the average temperature of the universe, which is the cosmic microwave background radiation temperature, then it will actually absorb the left behind radiation of the Big Bang, and therefore it will grow in size and it will last longer than the current lifetime of the universe. A smaller black hole, a hotter one, will evaporate, and therefore it will eventually die in a large explosion. So, yes, small black holes do evaporate and they will eventually die. Larger black holes, depending on how large they are, have a lifetime that can be longer than the current lifetime of the universe. So that's the strange thing about black holes. Large ones are actually very cold. Now, when black holes explode, what comes out of it? What comes out of a black hole is thermal radiation. It's called black body radiation, and it is basically made up of subatomic particles, elementary particles. So it's a random hadronization. It gives off hadrons and photons, and even antimatter. So that's what comes out of a black hole when it explodes. That's what is Hawking radiation. So that's how a black hole ends its life in an explosion of Hawking radiation. Divyansh asks, can you explain what are brown dwarfs and how they are made? We say that if a body has a mass lower than a minimum mass required for fusion, it's a brown dwarf. What is this minimum mass? And how do we distinguish between a planet and a brown dwarf then? Good question. So, like you said, a brown dwarf is a large enough gaseous planet that does contain hydrogen mostly, and it is not massive enough to sustain thermonuclear fusion. So, it is not able to sustain a thermonuclear fusion reaction, which is what powers the stars. That's what gives off the light. And therefore, these stars are somewhere between a planet and a star. So, what is the minimum mass? The minimum mass of a brown dwarf is, I think, 16 times the mass of Jupiter. So, that is the minimum mass required for something called the fusion of deuterium. So, in a regular star, you have fusion of hydrogen into helium. Now, a deuterium is an isotope of hydrogen. Hydrogen has a proton in the nucleus and an electron that goes around it. Deuterium has a proton and a neutron in the nucleus and an electron that goes around it. So, when the mass of a gaseous planet goes beyond 16 Jupiter masses, that's where it is possible for it to sustain the fusion of deuterium for some time. And that's what can give off some kind of energy. So it is like lukewarm. It glows faintly in the magenta-ish color range, right? And it is reasonably hot, but it's not hot enough like a star. So the mass range of a brown dwarf is between 16 Jupiter masses and approximately 18 Jupiter masses, which is the minimum threshold for a gaseous object to become a star and for thermonuclear fusion of hydrogen into helium to ignite. So that is the mass range of a brown dwarf between 16 Jupiter masses and about 80 Jupiter masses. And that is what distinguishes a planet from a brown dwarf. So below 16 Jupiter masses, you have a gas giant planet. Above that and below 80, it's a brown dwarf. Above 80 Jupiter masses, you most likely have sustained thermonuclear fusion of hydrogen into helium. And that's the lowest mass a star can usually have. Uditanshu asks, the Big Bang theory says that the universe was an infinitely dense point called a singularity, and there was no concept of space and time. But the singularity point must exist in a space. So, is the Big Bang theory misleading? Well, here's the thing about this Big Bang singularity. We don't know if it was a big bang, if there was a singularity at the big bang, or if the space time was compressed into a minimum quantum of space time. We don't know what it exactly was, but assuming it was a singularity, it wasn't in any point in space or time. The entirety of the universe was compressed into the singularity. So all of space time was within the singularity. And the singularity, we don't know in what it was. Was it in some other dimensional space time or not? We have no idea of knowing. As far as we know, it is the only thing that existed anywhere, and the entire universe was within it. And something caused this singularity to expand violently, superluminally, and that's what gave rise to the universe. So it's like asking, where did the Big Bang happen? What was the direction? There is no direction. The Big Bang was everywhere. Everything came out of the Big Bang. And similarly, this singularity was everywhere. Everything that we know of, everything that we can observe was within this singularity. So this is the best theory that we have. The singularity did not exist in a space. All of space and time was within the singularity. So this is the best theory that we have, and this is the it gives us it explains to in the best way possible what we observe in the universe, and therefore this is as far as we know today, this is the correct theory of the evolution of the universe. So I would not say that the Big Bang theory is misleading. It is our interpretation that needs to basically encompass what really happened. There was no space time outside of the singularity, as far as we can tell. Everything was within it. So I hope that clears this doubt. Okay, Prathamesh asks, what is the Aurora Borealis? What is its significance? Does it only happen in the northern region or anywhere else? Right. So the Aurora Borealis is the northern lights. There is something called the Aurora Australis, which is the southern lights, which happens near the South Pole. Now, what exactly is this? So it's what you observe in the night sky. You have these curtains and shimmering sheets of light. Usually, they are greenish, pale greenish, or pale pink in color, and these are waving sheets or streamers of light. And sometimes you have different colors. You have purple, you have blue as well. Sometimes it's white. So what exactly is this is the question. So these auroras, they begin in the sun. So the sun has something called, the sun itself has an atmosphere. And the sun has a very powerful magnetic field, which causes these big loops that are called solar prominences. So these are big loops of gas that go out of this sun's corona and come back inside. So these are magnetic field lines which cause these big gas loops. And sometimes the magnetic field lines pinch off, and this results in a big coronal mass ejection, which is a big explosion kind of, or ejection of solar gas, highly intense, very hot gas of plasma, essentially charged particles that are ejected out of the sun. And there is this constant solar wind that's coming out of the sun. And when this solar wind, which is the highly energetic charged particles, plasma, when this solar wind interacts with the magnetic field of the Earth, that's when you have this phenomenon, which is the Aurora Borealis or the Aurora Australis. So the magnetic field of the Earth is kind of, you could consider it to be kind of weak near the poles, near the North Pole and the South Pole. And that's where these charged particles are able to basically enter the atmosphere and interact with the gas of the atmosphere. So it is the interaction of these particles with oxygen at various altitudes and various pressures that causes these different colors. And it's also not just oxygen; it's also nitrogen that reacts with these charged particles. So it is the reaction or the interaction of these charged particles with oxygen and nitrogen at various altitudes and various pressures that causes these different colors and these light shows that we observe near the poles. So that is basically what aurora is. And the Earth is not the only planet that has auroras. We have observed auroras on Saturn as well, and I think on other planets as well. So it's something that occurs wherever you have gas and wherever this gas is able to interact with the solar wind, because of the magnetic field of these planets is the weakest near the poles. So that is what an aurora is. That is the significance. It is the interaction of the solar wind with the atmosphere, with the gases in the atmosphere of the Earth. Okay, Sagar asks, why don't asteroids hit the sun? Asteroids do hit the sun. The sun is just so massive that it doesn't register at all. The impact is it's not noticeable. So the sun is, I think, more than 98 or 99% of the mass of the entire solar system. And an asteroid is a negligible mass compared to that. So asteroids do hit the sun from time to time. You even have comets that hit the sun or get fragmented by the sun. And it's something that you can't really observe, because if it does hit the sun is so bright, so luminous, that you will not be able to observe something so small and something so dim hitting the sun. But there's no reason to believe that it doesn't happen. We have seen comets going past the sun, trying to go around the sun in an orbit, and these comets do get fragmented by if they come too close to the sun. And if that happens, some fragments will indeed hit the sun, depending on the trajectory. And the same would happen to asteroids as well. So yes, asteroids do hit the sun. Comets also do hit the sun. There is nothing in the laws of physics that precludes such a thing from happening. So this is by Indrayuddha. With today's technology, are we capable enough to divert a large incoming asteroid? In short, can we survive a dinosaur-like situation? A good question. So what happened to the dinosaurs is that an enormous asteroid or comet impacted the Earth. It is believed to be around 10 to 15 kilometers in diameter, an enormous space rock which hit the Earth in Mexico's Yucatan Peninsula. We have found the impact crater. It's called the Chicxulub impact crater. So this is what happened during the time of the dinosaurs about 65 million years ago, and it caused a disastrous cataclysm on the planet, and a great number of species, a significant majority of the species of animals and plants on the planet were wiped out because of this. A few survived, and most of the dinosaurs died out in this. So this is the prospect that looms upon humanity, because sooner or later this sort of thing is going to happen again. So are we capable enough to divert such a large incoming asteroid? So how would we do that? The popular science fiction movie strategy to deal with this is to launch a nuclear missile at this incoming asteroid. However, you find that even if you were to detonate a big, very powerful nuclear bomb, maybe 50 megatons or so, at near an asteroid, it would merely fragment the asteroid. And instead of one large asteroid hitting the Earth, you would have a bunch of fragments hitting the Earth in multiple locations. So it's not the best strategy. I think the best way to divert an asteroid is to use something called a gravity tractor. So what you would do is you would send a spacecraft near the asteroid, maybe a year or so before it's supposed to intersect with the Earth's orbit, and you would use the gravity of this satellite or spacecraft to slowly nudge the incoming asteroid away from the trajectory of the Earth's orbit. So this is called gravity tractor, or so that's what could basically deflect it just enough so that it will miss the Earth. So this is theoretically possible. Have we ever tried this on an asteroid just to see if it works? We have never tried it. And recently, I think there was some analysis done whether we are able to prevent something like this happening, and it was found that as of today we don't have the ability to prevent a massive asteroid strike. So as of today, with the technology that we do have the technology theoretically to deflect an asteroid, provided we know it's coming and we are able to predict this. The thing is that there are so many asteroids in the solar system. Many of them are near Earth asteroids. Some of them are of particular concern further down the line, 10, 20, 30, 50 years down the line. So there are these space watching programs, asteroid watching programs that keep track of these potentially dangerous asteroids. But there are so many asteroids in the solar system, millions and millions of them. It's impossible to try to know about every one of these. So there's always the possibility that something will come out of somewhere and could possibly pose a significant danger to Earth. So in short, as of today, we basically don't have the capability to divert a large incoming asteroid. If today, if astronomers were to find suddenly a new asteroid that's going to hit the Earth in 6 months' time, we are most likely doomed. Most likely, it will be very difficult to scramble a space mission, in time to do something about this. If you find something that's going to happen maybe 1 year down the line, it may give us a better chance. Ideally, we want something to be known at least a few years beforehand so that we can plan properly. And in that case, it should be possible to divert or deflect an incoming asteroid. But at short notice, it's basically impossible. So one hopes it doesn't happen anytime in the near future. This sort of thing happens once in about 65 to 100 million years. So it's been 65 million years since the last time it happened. So it's best that we are prepared for this. So that's the answer, sir. Okay, Akash asks, how can we detect exoplanets hundreds and thousands of light years away and know their size, density, mass, etc.? Yet we can't figure out what is the gravitational anomaly that affects the orbit of Pluto in our own solar system, despite being so close comparatively. Excellent question. So how do we detect exoplanets hundreds of light years away? So there are a couple of methods of doing it. One of the methods is to observe a star and try and see if there is any periodic dimming of the star. So if a star is observed to dim regularly in a periodic manner, it would indicate that there is something that comes between us and the star, between the line of sight, and that is something that indicates a planet. And depending on how far the star is and how much is the dimming of the light in a periodic manner, we can actually determine the size of the size of the planet that is coming between us and the star. The other one is to detect whether there are any oscillations in the period and things like that. So there are certain indirect ways of observing whether there is an exoplanet or not. And once you know about an exoplanet, if it transits a star, you can actually try and detect the spectra of light that come from there, and then we can determine roughly the kind of composition, etc. it has. So this is a very hit and miss kind of thing. It basically we can do this only if the plane of the orbit of this exoplanet is exactly between us and its parent star. So we have detected thousands of exoplanets, but we have missed millions because they are not so inclined. So the statistical likelihood is basically one in, I don't know, at least thousands or maybe millions. And yet we have found thousands. Now, when it comes to the gravitational anomaly that affects the orbit of various of Pluto, etc., so we have detected that there seems to be something massive beyond the orbit of Pluto that is causing certain Kuiper belt objects to have strange inclinations, and it's causing them to behave strangely. So there is the possibility that something is lurking out there, but we are talking about something massive but something dark, and that's so far away, and there is nothing that it is transiting. So if there was something between the earth and the sun, then we could observe it transiting the sun, and it would be illuminated by the sun's light. But if something is that far away, way beyond the orbit of Pluto, then the sun's light over there is extremely dim. And if it is a darker body or a redder body, it's almost impossible to detect it at such an incredible distance. And there is even the hypothesis that it could be a primordial black hole of some sort, in which case it's absolutely impossible to detect it. And yet it would have the same gravitational effect as a planet of the same mass. And these are the reasons why it is so hard to detect it. We may never be able to detect it, even if it does exist. The planets that have been detected thus far have been gas giants, and Pluto itself is quite bright because its surface is quite icy and very reflective. So the objects we have been able to detect thus far have been very bright, either large and bright or small and shiny. And it is known that there are certain objects that are quite dark. That are coated with hydrocarbons of some kind. Some of these are full of carboniferous material, etc., and these will be quite dark. So these are some of the reasons why it's very hard to detect an object like that, especially at such a large distance away, way beyond the orbit of Pluto. So we may be able to find it if it does exist, or we may perhaps never be able to find it. If we do find it, it will be great through a great deal of luck more than anything else. Okay, this is from Deepak Singh Rana. Namaskar, Deepak. Kindly explain the role and importance of the Large Hadron Collider, CERN, in modern science and its future of humanity. What led to the scientists to put Lord Nataraja's statue outside the facility? As there are some ongoing conspiracies about the link of that statue and the activities going on there, I have been asking this question since the last 7 live sessions. I am very sorry I didn't see your question. I found it, thankfully. So please clear this up if you know anything. Okay, Deepak. So, what is the Large Hadron Collider? The Large Hadron Collider is a powerful particle accelerator. It accelerates protons, mostly charged particles, protons, to almost the speed of light. So it accelerates them to extremely high velocities, and it imparts enormous amounts of energy to these particles. And it collides them head on. So proton beams colliding head on. And when two protons collide in this manner, they get smashed up, and a whole bunch of debris flies out. And the debris that flies out depends not just on the mass of the two protons, but also on the energy that is imparted to the protons. So a lot more comes out because of the E equals mc square relationship. And it is hoped that it is by observing these collisions and these high energy wreckages of particles that we may find some new physics or some new phenomena or some new particles. And this super collider is able to, I think, create millions of collisions per second when it is running and fully operational. So this is what has enabled us uh, to discover the last missing link in the standard model of physics, which was the Higgs boson, which is the gauge boson that imparts mass to various subatomic particles. So without the Higgs boson, there would be no mass in the universe, and the universe would be a very different place. So this is the one major discovery this particle accelerator has done. So that's what the Large Hadron Collider is. It is the most expensive scientific instrument ever built. It's the most powerful collider ever built, and it has succeeded in discovering this last missing piece of the standard model. Is there any conspiracy going on there? None that I know of. Yes, there is a statue of the Lord Shiva, Lord Nataraj, outside of CERN, and I think it has been placed there as tribute or homage to the god that is believed to be the creator and eventual destroyer of the universe, uh, which is kind of in line with the Big Bang theory. I mean, the creation at least is in line. We don't know how the universe will end eventually, but if it is indeed destroyed at some point, it is, well, one could say that it is the Lord Shiva who does this. So that is the only reason why the god has been put there. He's the creator and the eventual destroyer of the universe. So it is in honor of this great god that his statue is put there. There is no link, there is no scientific reason for putting the statue there. There is no link between the statue and the scientific experiments that are going on inside. And as far as I know, there is no conspiracy of any kind in CERN or in the Large Hadron Collider. So that is the best I can answer this question. I know that you're looking for some conspiracy link. I am very sorry. I don't have any answer to any conspiracy. I don't know of any conspiracy or any scientific link between what's happening scientifically and inside this facility and the statue. So as far as I understand, it's just to honor the great God who creates and eventually destroys the universe. That's all I can answer. Okay, thank you. Okay, Somen asks, what are your views on the global warming phenomenon? Is it a natural process by being accelerated by human activities, or is the situation really very acute as portrayed? Will mass electric vehicles adoption stop global warming? So global warming is a reality. Global warming does happen. It's been happening for ever since the planet was born. Global warming has been an ever present feature of planet Earth from the very beginning. And the Earth's atmosphere and climate, etc., has seen massive changes over the eons. So it is a natural process, yes, but do human activities accelerate or affect global warming? Definitely yes. And even if you look at the past 20, 30, 40,000 years of human history, there has been significant change in the climate. So there has been a massive ice age, the last glacial minimum, which was around 20,000 years ago or so, before today. There was the Younger Dryas period, which was a sudden surge of cold weather, which happened about 13 to 12,000 years ago. And then there is the Little Ice Age, which happened a few centuries ago. And now there is this global warming that's happening. So this is something that keeps happening over time. But yes, the human activities are indeed, as far as we know from the data that we have, the human activities are indeed causing and speeding up the rate of global warming right now. So this process began with the Industrial Revolution, when the Western world started emitting carbon into the atmosphere in large quantities. And today we have a great deal of excess of all this, which has been released into the atmosphere. And this is causing the effect of global warming, because there are greenhouse gases, etc., that are part of this. So yes, it is definitely something that's happening. Can we stop it? I doubt it very much. It's going to happen whether we like it or not. We can try and slow down our contribution to global warming, which even that is quite difficult to achieve, because every country does what is best for itself and its national interest, and it's very difficult to achieve certain targets. So it's going to happen whether we like it or not. The situation, I don't know how acute it is, but yes, we are moving towards a time in which the temperatures will on average be a couple of degrees, maybe 2 or 3 degrees higher than what they used to be in the past. So that is a significant change, yes. And it's going to cause a great deal of changes in the climate, in the sea levels, etc. Very low-lying countries like the Maldives and certain South Pacific islands may entirely disappear. Coastal regions and coastal cities may be greatly affected by this rise in sea levels. So yes, we will see this in the coming decades, maybe century or so. Yeah, it will happen. Will the adoption of electric vehicles in massive numbers stop global warming? Well, it all depends on how we are producing electricity. Even if we stop using these combustion engines and stop using petroleum and gasoline, diesel, petrol, etc., but if we are still generating electricity using the burning of coal or any such dirty method, then even if we adopt electric vehicles worldwide, it's going to make no difference whatsoever, because we are still generating electricity by burning coal or by burning some other fuel. So the best way to slow down this process is to use renewable energy, solar energy, wind energy, hydrothermal energy, etc. That would be or nuclear energy. So these are the ways in which we can possibly slow down the global warming. But just adopting electric vehicles will really make no difference as long as electricity is produced the way we currently are producing it to the largest extent. Because I think most of the universe of the electricity produced worldwide, I think a major portion of it is produced by burning coal, and that is just as bad as using a diesel or petroleum burning vehicle. So that is the key. It's to use sustainable sources of energy. Okay, this is by Riddhi. If there are galaxies which recede away from each other faster than the speed of light, what will be the time dilation accordingly? A good question. So, time dilation is something that happens when you go at a when something travels at a relativistic velocity, which is a significant percentage of the speed of light. So, if you have two twins, one who remains on Earth and the other twin goes on a rocket which travels, let's say, at a tenth of the speed of light, and that person who is in the rocket may experience, let's say, a journey of, let's say, 1 year. And when this person comes back to Earth after traveling at the speed of zero point 0.1 the speed of light for 1 year, he or she may find that their twin has aged much more than 1 year, and how much this twin has aged can be calculated using the principles of special relativity. So this is called time dilation, right? So when something travels at a significant percentage of the speed of light, you experience time dilation. Now we know that there are galaxies and portions of the observable of the universe that are receding away from us at the speed of light or faster than the speed of light, which means we can never observe them again. Now it's not happening because these galaxies are traveling within space-time faster than the speed of light. It's because the space-time itself is expanding faster than the speed of light. So there is this speed limit in the universe, which is the speed of light, but it doesn't mean that the space-time itself cannot expand faster than that. Space-time itself can expand faster than the speed of light, in which case there is no time dilation whatsoever. The time dilation only happens when you're traveling within space-time at a significant portion of the speed of light. But if you are embedded inside space-time and that space-time itself is expanding that fast, then there is no time dilation whatsoever. So it's something that's quite complicated and hard to wrap your mind around. But that is one of the strange things about the universe. That's one of the mysteries of the universe. So superluminal expansion is indeed possible, and it does not violate the speed limit as long as it is space-time itself that is expanding this fast. And we know it is in certain portions of the universe. So the observable universe is about 93 billion light years in diameter. And every minute as we speak, there are stars and galaxies that are basically going outside the observable universe because they start to recede away from us faster than the speed of light. So that's happening as we speak. The cosmic horizon is shrinking. Eventually, the only thing that we will be able to see in the universe will be just a local cluster of galaxies. And maybe eventually it will just be our own galaxy combined with Andromeda. So that's the thing. That's the future that awaits us, provided we stick around as a species for another 5 billion or so years, in which case things will be very strange and very interesting. Okay, Dungar Singh Chauhan. If nothing can escape black holes, then why don't they just suck up the entire universe? So it's like saying, if there is a very big fish, why doesn't it suck up the entire ocean? Right? So even if nothing can escape a black hole, it doesn't mean it's going to suck up the entire universe. Right? a black hole is a certain size and it has a certain event horizon, and it absorbs permanently or more or less permanently only something that crosses the event horizon. If something is outside the event horizon, it doesn't suck it up. The black hole is not like a vacuum cleaner. It goes everywhere and sucks everything inside. It's not like that. A black hole can sit in its corner of space time quietly for almost forever without ever coming into without ever interacting with anything else, if it is in such a location of space time where very less there are very less stars or galaxies around. So so even if you look at the supermassive black hole at the center of the Milky Way, it's not really active. It's not really sucking anything in. It is an enormous, supermassive black hole. Its mass is of the order of millions of times the solar mass, and yet it's sitting quietly at the center of our galaxy. It's not doing anything. It is basically holding the galaxy together, and it's not sucking in any matter because nothing is, as far as we can see from here, crossing the event horizon. There are a bunch of stars that are very close to it, and they are moving very rapidly because of the proximity to this massive object. And yet they're not being sucked in. They are simply orbiting the black hole. So a black hole is not necessarily something that's going to vacuum clean everything and suck everything in. It can just sit there essentially forever and not suck anything in, depending on where it is located. So that's how it is. So I hope that answers this question. Okay, I think I've taken 19 or 20 questions. Let's take some live questions now. And I saw a question earlier. I don't know where it is now, but somebody asked me that, are the dinosaurs all extinct, or are some dinosaurs, did they all die out 65 million years ago? And the answer is that there was indeed a disastrous cataclysm 65 million years ago, the Chicxulub impact event, in which the majority of dinosaurs died out. But a certain category or class of dinosaurs survived, the avian dinosaurs, and their descendants are still alive. Those are the birds. So the birds are dinosaurs. The dinosaurs who lived about 65 million years ago had feathers. Most of the dinosaurs that is now found seem to have had feathers. Even the great T-Rex may have had feathers. So birds are essentially nothing but dinosaurs. These are the dinosaurs that survived that horrific day. And so the closest living relative to the T-Rex is the common chicken. So dinosaurs did not all die out. The non-avian dinosaurs died out. They all perished, but the avian dinosaurs survived, and they are still around today. Your favorite bird is a dinosaur, whether it's the peacock or the turkey or the chicken or the hawk, eagle, whatever it is. These are all descendants of dinosaurs. These are all dinosaurs. These are living, breathing dinosaurs. Isn't that interesting? Okay, let me find some interesting questions. Thank you, Vineet. Appreciate it. Thank you very much. Okay, this is by Jyoti. What do you think about the technology required for interstellar travel faster than the speed of light? What are the different ways in which we can achieve it? There are a couple of ways, hypothetically, perhaps, possibly, that we could conceivably try and travel faster than the speed of light. One is the favorite staple of science fiction, which is the wormhole, which is essentially something that connects two far apart regions of space-time together. It's like a tunnel through space-time, and it connects two very distant regions of space-time together. So theoretically, it may be possible. It is something that tends to pinch off and close into two black holes. But if you have something like the theoretical, hypothetical cosmic strings, then cosmic strings could possibly keep a wormhole open. And if it is large enough, wide enough, then it may be possible for human beings to travel through one. So that is one theoretical hypothetical possibility of traveling faster than the speed of light, or basically bypassing the speed of light. The other one is the warp drive, which seems to perhaps be possible. There are certain solutions of Einstein's equations of general relativity which may make it possible theoretically to construct a warp drive engine, which would require immense amounts of energy, but it may hypothetically or theoretically be possible. So these are two possible ways in which it may perhaps be feasible to travel either faster than the speed of light or to bypass the speed of light itself. But we are nowhere close to doing anything like this. We are basically stuck at below the speed of light, and we are just trying to construct better rocket engines, or maybe to uh, create technology such as the light sail, which may allow us to accelerate to relativistic speeds. So that is the best we can think of right now. This is all firmly in the realm of science fiction, either wormholes or warp drives. But theoretically, it may be possible. Okay, Manima asks, can life exist without carbon and oxygen? It may be possible. It is not unconceivable that there may be different kinds of life, or maybe non-carbon based life, maybe silicon based life forms. It is possible. So the search for life is primarily something that we do in the so-called Goldilocks zone around stars, which is the zone at which it is possible to have liquid water or flowing water. So we are basically trying to find exoplanets that are in that habitable zone around their parent stars. But it is possible uh, that there may be other forms of life as well. For example, you have this moon of Saturn called Titan, which is rich in hydrocarbons. It has a very interesting cocktail of hydrocarbons and very interesting chemistry out there. So it is conceivable that you may have non-carbon based and non-water based life over there, and it could something like that could happen on other planets as well, on exoplanets as well. So it is not necessary that all life has to be based on carbon and oxygen only. There could be other forms of life which we may not have thought of. It is definitely possible. Okay, Yash asks, please tell us about tectonic weapons. Is it possible to create earthquakes artificially? Well, I think if you detonate a powerful nuclear weapon underground, it is going to cause something like an earthquake. So that is one way of having a tectonic kind of effect. As far as I know, such weapons don't exist as far as I know. If any such research is being done, it is being kept under wraps, and it would need immense amounts of energy to actually shake the Earth's crust in that manner. So, as far as we know, as far as the publicly available information is concerned, such weapons don't exist. Is it possible to create such a weapon? Definitely. We could use a nuclear weapon or some other form of energy, very energetic weapon or process, in which case you could have something like this. So it is not science fiction. It is definitely possible if you can harness that amount of energy and use it to vibrate or shake or disturb the crust of the earth. It is possible hypothetically. Does it really exist as of today? I It is very doubtful. If it does exist, it is highly classified. So that's what we know about this hypothetical technology. Okay, do we have something else? Okay, Dhyana asks, can we put an artificial satellite on an asteroid? That could help scientists save fuel as it can travel on the asteroid forever. Well, satellites are typically to be placed in orbit around our planet so that they can perform a variety of tasks, whether it is remote sensing or telecommunications or whether it is broadband or something. So you would typically have a satellite in low Earth orbit around 100 kilometers above our planet, or in polar orbit, or in geostationary orbit, or something like that, right? So there's a variety of orbits that you could place a satellite in, and you don't want to have a space rock orbiting the Earth at that sort of altitude. You just don't want to have that. So it would not make a great deal of sense to put an artificial satellite all the way on an asteroid, either sending a satellite all the way there, in which case it would not serve any purpose for us here on Earth, because the asteroids are really, really, really far away from the Earth. The asteroid belt is between the orbits of Mars and Jupiter, which is a very large distance away from Earth. So it would not really serve any purpose for us here on Earth. And to bring an asteroid here near Earth and put a satellite on it would basically be pointless, as we can just put a satellite in Earth's orbit itself. So we would basically save the most amount of fuel by placing a satellite in Earth's orbit instead of trying to involve any kind of asteroid in this matter. So a satellite can, for a very long period of time, remain in Earth's orbit. Could happen for centuries if you put it in a certain orbit. So I hope that answers your question, Diana. Okay, do we have anything else? Okay, Manima asks, space colony on Mars or on artificial self-sustaining planet, aka mega satellite, which seems more realistic? I would say a colony on Mars is more realistic because it would take less resources than constructing an enormous mega satellite. So to send people on Mars, you would need to have a large rocket or a number of large rockets, which can reasonably easily be constructed here on Earth. And once these people reach Mars, they could use the resources on Mars itself to construct a colony. So you could possibly have some robots that do mining on Mars and extract metals, etc., and construct a colony or something like that. So that is definitely something that could happen in the next 2-3 decades, possibly. But constructing a mega satellite would basically take a great deal more resources than just sending people to Mars and doing this there. Therefore, it is much more realistic to have a space colony on Mars with a few people than having a mega satellite anywhere in the solar system. So the Mars colony is much more feasible than a mega satellite. Okay, let me take a couple of more questions. So this is a similar question. Why can't we just make an artificial Earth like a spaceship instead of terraforming a whole planet? We can get raw materials from different planets and convert them into things we need. While it would need a great deal of power and engineering capability to be able to take raw materials from various planets and and construct a whole new planet out of that. That would that would basically need you to be most likely a Kardashev type 2 civilization. You would have to go beyond a Kardashev type 1 civilization. So a type 1 civilization is one that can harness the entire resources of its home planet, and a type 2 civilization is one that can harness the entire resources of its home solar system. So to do what you're proposing, one would need to be somewhere between type 1 and type 2. So it is not easy, it's extraordinarily hard to achieve that level of engineering capability. So it is way more easier just to go to another planet and try to modify its atmosphere to make it more Earth-like and more habitable for human beings than to construct a whole new planet out of raw materials. So I think it's easier to try and make a planet like Mars more habitable for human beings. Okay, Sovik asks, why can't we construct a colony on the moon instead of Mars? Well, you're right. It's easier to construct a colony on the moon. It's right next door. We can reach the moon in a couple of days, depending on how powerful or how fast your rocket is. And yeah, it's close by. So, and it takes almost a year to reach Mars one way. So there is a much greater risk in that amount of space travel, and it's much easier to construct a colony on the moon. The problem with the moon is that its gravity is very small. So if you weigh 60 kilos on Earth, you will weigh only 10 kilos on the moon. Secondly, there is no atmosphere on the moon, so you would always need to be inside a spacesuit if you ever went outside your space colony. And the low gravity has harmful effects on the human physiology in the long run, which is well known. The gravity of Mars is lower than that of the Earth, but it is still much greater than that of the moon. So it is a better long term prospect for human habitation, way better than the moon. And it does have an atmosphere, which can hopefully someday in the future be augmented and made more Earth like if we can develop that capability. So these are the reasons why the moon is not that attractive a target for constructing a long-term space colony than Mars itself. Mars would be a much better prospect for the long-term future of humanity as a secondary home for our species. The moon is not anywhere close to the kind of benefits that Mars would give you. It's much larger. There are many more resources. There's a lot of water there. So Mars is overall better than the moon. Okay. Okay, let me take one or two more questions. Okay. Is there any possibility of black rays? I have never heard of black rays. I'm very sorry. I don't know what that is. Uh, Black rays. I can't imagine what that could be. Sorry. I'll try and look it up. And if something like that exists or is hypothetically possible, I'll try and answer that in the next session. I apologize. I don't have an answer to this question. Do I believe in aliens? I believe it is very likely that that life does exist on other planets, maybe even within our own solar system. It is statistically highly likely because statistically there are more than 10 raised to 20 at least exoplanets in the universe, 10 with 21 with 20 zeros behind it. So even if life is a 1 in a million occurrence, you still have more than a trillion planets with life on them. And even if intelligent life is a 1 in a million thing, you still have billions of planets that would have intelligent life. So I think it is extremely likely that aliens do exist, intelligent life forms. The only question is, why haven't we met any or detected any signs of them? So that is the Fermi paradox. There are a number of hypothetical answers to it. So that's a whole different question. But do I believe in aliens? I think it is extremely likely that aliens do exist. So that's the answer. Okay, let me take one more question. Okay, it is by Ayush Rai Jaiswal. Can we use light source as a fuel so that we can achieve the speed of light? Well, there is something called radiation pressure. So just as if I punch my fist into my palm, it's going to impart a force on my palm. The same way, the light that's hitting my palm also does exert an actual pressure on my palm. So there is something called a light sail, which can hypothetically be used to accelerate objects to a significant percentage of the speed of light. A light sail is something that uses the pressure of light itself. So you have a very thin and very light reflective sail kind of object, which is usually made up of some kind of metal. And if you were to focus laser beams on it, then the pressure that this laser beam imparts on the light sail can very quickly accelerate that light sail to maybe 10 or 20% of the speed of light. So that is a technology that could be achievable in the next 10 or 15 years. So there is a project that is right now ongoing that could possibly achieve this in the next decade or maximum 2 decades. But can we achieve the speed of light itself? No. There is nothing that can achieve the speed of light. The faster you go, the more massive the object becomes. That is called that is the thing about relativity, that the faster a mass travels, the more massive it gets. And that is why it is impossible to achieve the speed of light, because the mass would basically become infinite. So there is nothing that can conceivably, according to the laws of physics, accelerate an object to the speed of light. But light sails can theoretically achieve 20 or even 30% of the speed of light. So that is the best we can do within the laws of physics as we understand them as of today. Shall I take one more question? Okay, one final question. Okay, 95% of the universe is non-physical. Dark matter and dark energy, both as of now, are non-physical effects. Well, unfortunately, that is not the case. 95% of the universe is invisible to us. It is physical because it has a physical effect. And that is how we know it is there. Dark matter interacts via the gravitational force, via gravity, and we can see its physical effects. It does cause gravitational lensing, which is a physical effect. So we know it is there. It is a physical thing, but we just don't know what it is made of. So dark matter is about 20 or so percent of the composition of the universe, roughly. Dark energy also has a physical effect. It causes the accelerating expansion of the universe. It acts like an anti-gravity kind of force. So that also is quantifiable. It is physical. And this unknown energy is about 70% of the entire mass energy composition of the universe. So these are physical quantities. These are physical things. These are not unphysical or non-physical effects. So science and physics is concerned with physical phenomena, observable or measurable phenomena. And dark matter and dark energy are both quantifiable, measurable, and observable in one way or the other. So these are physical effects or materials or matters or forces, whatever they are, right? So we don't know what it is, but we know it is there. So it is definitely very much physical. So I hope this clarifies this particular matter. All right, my friends, I'm done for the day. Thank you very much for participating. Very interesting questions. And we will continue doing this episode week after week. So we will have one more episode about this particular topic once again next week. But for today, thank you very much for your viewership. Thank you for participating. Thank you for your comments. Thank you for your questions. And I will see you in the next episode. I wish you a good night, a good day wherever you are. Take care. See you. Bye.